Hello everyone, welcome to this talk about how to make releases safer in Baidu. I am Pingping, a senior engineer from Baidu SRE. My work is focused on the release efficiency and quality. My partner, Chen, a data architect, focuses on the anomaly detection and analysis based on data mining. Baidu SRE is responsible for the world's largest chat search engine. Baidu has over 100 billion chat web pages and many other products. This talk focuses on the quantity of release. Product iteration speed promotes success. Rapid trial and error can improve the product experience. As the world's largest chat search engine, the business scale of Baidu has always been growing rapidly. And the release times is also growing. Last year, there were 3,000 each month on average, such as releasing new features, bug fix, and improving the system performance. Changes are accompanied with risks. Last year, 54% of the service faults are due to release. Release has become the top killer of service stability. When you want to search for the weather, if it rejects or displays chaos, or run out of memory, or responds slowly, it's most likely because the release process is out of question. And these bad cases have been a lot in history. How to solve it? On the one hand, we should improve the code quality to reduce the problem of leakage to the release process. This is mainly the work of developer and tester. On the other hand, we should reduce losses as much as possible during the process of release. And this is mainly the work of SRE, and it is also the main content of this talk. In a era of manual release, the release of a program used the incremental release model, not the entire package release. Different developers modify different files and then submit them to different testers and SREs. This brings many problems leaking into the release process. For example, first, it is impossible to fully simulate the production environment during testing, so the test is inaccurate. Second, it is hard to roll back to a specific version to stop loss quickly. So the solution is package release. This is mainly done by developer and tester. We summed up 7 major problems of manual release. First, mistyping. For example, you originally intended to remove one file, but typed the wrong command to remove all the files. Second, stage delaying error. For example, you release all the IDCs at the same time. Third, you choose the wrong concurrency. For example, you may restart all instances at the same time. Once the program is abnormal, your service may be unavailable. 4, no checking. Many people always have look in mind, such as, I just modified one line of code, I guess it's okay. But the truth is, it's always wrong. Okay. 5, insufficient coverage of indicators. Less than 10 indicators can be checked by hand. And it always takes a lot of time to find out the indicators on the monitor and figure out what's going wrong. 6, inconsistent checking standards. Often, the experienced SRE know what to check and how to check. So, the new SRE always make a mistake. 7, it is inconvenient to stop or roll back a release, because we SRE need to log into the terminal and execute a lot of commands. It always takes more than 10 minutes or 30 minutes to stop loss. It's too long. In order to solve these problems, SRE have done these things. The first thing is to divide stages reasonably. The principle is to minimize losses as much as possible. First, from sandbox to production, at the yellow color, there will be no loss after sandbox. Second, from the IDC with the least requests, as the blue color. Even if there is something wrong with this IDC, we can cut its flow to the other IDCs quickly. Third, we can, from a few instances to more instances, at the stage 1 to stage 2, or stage 3 to stage 4. Usually, we first deploy 1% of one IDC, and then deploy 99%. The second thing is to build our release platform. In the past, we need to type a lot of commands. It usually takes more than 30 minutes, and SRE often make mistakes. With this release platform, all the work can be done at one button in less than 10 minutes. For example, the green button is to launch a new release. The red button is to roll back. The blue button is to freeze in a special time, such as the Congress of China or APEC. It can stop all the releases and disable the new release to avoid the risks by release. In addition, we can query the release history in the past few days or the releases launched by somebody. And also, we can query the progress of the current release. With a reasonable stage division, we build automatic checking after each stage. It will automatically check if there is an alarm and decide to stop. Usually, the alarm is based on static threshold set by SRE, and only the experienced SRE know what to check. At the same time, the plan platform will monitor the indicators throughout the process. Once a major fault occurs, it will stop all the release. There are 3 types of checking. First, availability indicators, such as the daily availability. Second, system-related indicators, such as CPU used, memory free, call dump, or queue length. Third, business logic indicators, such as the key elements of the result page. For example, when you search for the weather of Singapore through Baidu, when you may be rejected on the left picture, but the normal result is the left picture, showing the temperature of today or the temperature of the following days. Last year, the recall rate is 57. It means that the rule-based checking really helped us and avoided a lot of faults in the past few years. Okay. But the new problems has come into being. The monitor indicators number of some module had reached 200,000, and the current checking can only cover the indicators selected by SRE, less than 100. And the static threshold is either too high or too low. For example, the indicator on the left picture has been obviously abnormal after release, but it has not reached the alarm threshold, so there will be no alarm. And the static threshold is not applicable to the periodic fluctuation. For example, the flow of daily requests is related with the user behavior. It may increase during the daytime and decrease at night. In addition, the static threshold is not applicable to the expected fluctuation. For example, the developer intended to improve the system performance and reduce the memory use. But SRE make it an alarm that the memory used dropped and should check what's going wrong. Therefore, we have introduced intelligent checking. It can train the threshold by machine learning with big data to avoid the problems of static threshold. And also, we have the ability to cover hundreds of thousands of indicators. We can cover more than 90% indicators. Okay, next, my partner Chen will introduce how intelligent checking works. Okay.
So as Pingping have said, the algorithm needs to accomplish the following goal. It needs to scan through all the indicators and also report the abnormal indicators. If the indicator is reported, then we will regard that the release is problematic, so the system can stop the release process in order to reduce the loss caused by this release. And because essentially this is just a procedure of anomaly detection, so initially we try to apply the anomaly detection algorithm in our alerting system to solve the problem. But soon we find that this problem is not that simple. For example, when we use anomaly detection in the alerting system, one major sources of alerts comes from the fact that when a metric changes abruptly, and we call that a sudden change, and there must be something wrong in the system. But in the sense of releases, this is not true. Many releases will modify the behavior of the whole system. So some or all of the metrics will change abruptly. So if we would just report all of these sudden changes out, and then maybe all of the release will be blocked. So we decided to do a comparison. We introduced the previous releases on the same module as a basic data. So we decided to compare the current release metrics against the previous release metrics. If we find that the current change is kind of similar to the change of the previous releases in the same module, we can decide that this might be okay. The release is not problematic. But on the other hand, even there is no any sudden change in the system, this does not mean that the release is okay, because many of the release will happen in specific times. For example, we know that in the morning, the user requests coming in, and the matrix usually just goes up. And in the evening, the user request just drops. So many metrics also drops. Because the release will take some time to finish its procedure. So when we compare the data after the release and against the data before the release, and there's always a step on the metric. So the sudden change is actually natural in this case. So if we perceive that the metric did not display any sudden change, it actually means that something wrong in the system. So we decided to use two sets of data as the basic model. One is the previous release in the same module, and one is the instance that have not applied the newly released as the control set. Here I would like to show you several examples. And in each example, we display three sets of metric curves. The first set is the current release curve, and the second set is the control set release curve, and the third set is the previous release curve. In the first example, we can see that the metric curve in the current release is quite similar to the curve in the control set. So we can decide that this case, the release is okay. And in the second case, we can find that the current release curve is actually quite similar to the previous release curve. So we can also conclude that this release is also okay. In the third example, we can see that the current release curve is different from both the control set and any of the previous release curve. So we can say that this release is problematic and should be stopped. So we come to the problem that how to measure the change on the curves in the current release, control set, and also the previous release. initially we tried to measure the changes on the instance individually, but soon we find that this is problematic. Here on the right side, we show a very simple example. In this example, the module contains three curves, three instances, and display the metric of these three instances. We can see that the two vertical dashed lines actually represent the start and the end of the release. And we can see that after the release ends, the orange line actually drops, and the red line actually increases, while the blue line actually keeps stable. If we compute the change on the instance one by one, and we will conclude that two instances actually have very big changes, and one instance is okay. But if we see the three instances collectively, we can see that the overall metrics actually do not change. The reason of this case is that many of the releases actually require a restart of the instances, and the restart will cause the load to redistribute among the instances, so the metric actually changes. So to solve this problem, we have to compare overall change of the instance set among different instance sets. So what we do is that we actually compute the average value after the release and the average value before the release. So this change becomes a delta. After we obtain the delta, we have to decide whether the delta is similar to the control set or the previous release set. So we have three deltas now. Delta 1 refers to the current release set, delta 2 refers to the control set, and delta 3 refers to the previous release set. Actually, all these three deltas are actually the average value, average difference of the instances. So we apply the Ttest in statistical hypothesis test to decide whether these three delta are similar or different. So if any of the comparison returns are similar, we can conclude that this release is okay. If both the comparison reports that they are different, we will see that the release is problematic. So we have conducted some offline experiments on the previous cases, and we choose 88 releases in our history, and we find that the algorithm will report 15 alerts on it. And 9 of the 15 alerts are actually correct. 1 of the alerts is incorrect, and the rest 5 actually reports alerts because there are lack of the control set data. If we introduce the control set data back, probably they will not report alerts. So in the next, I will pass the microphone back to Pingping.
Okay, thanks, Chen. Here is a real case at 25 April. You can see after stage 1 of business logic indicator, the CTR fail rate decreased, which means something was wrong, but did not reach the alarm threshold. So the rule-based checking passed, while intelligent checking detected this fault successfully and stopped this release. This is abnormal, and then we roll back and recover. Okay. 2 more cases. The intelligent checking can also detect system-related indicators such as CPU use %, the left picture, and also the decrease of the indicators on the right. Okay. When we roll back, it recovered. Okay, thanks to the cooperation of rule-based checking and intelligent checking, the recall rate has reached more than 80%. Yeah. Okay, let's look back on how we make releases safer. First, standardized development and testing. We used package release. Second, progressive rollout, minimize the losses as much as possible. 3, release platform. You can use it to launch a new release, roll back, freeze, or query history easily. 4, Plan platform can monitor the whole process and pause all the releases one button. 5. We have rule-based checking and intelligent checking. It can be more accurate and cover more indicators, so we can make our releases safer. Okay, that's all about my talk. Welcome communicating.